Hi everyone, here is a continuation of our 4.4b notes. Remember we did number 1 in the first video, and then we did only one other one. We go all the way down here. I think it was 5 or 6 that we did. Yep, we did number 5. Okay, so let's go back and see if we can do a few more of these. Okay, here is example 2. It says a closed cylindrical can holds 1 liter, 1,000 centimeters cubed of liquid. That's a volume. How should we choose the height and radius in order to minimize the amount of material needed to manufacture the can? Express your answer as an exact value in terms of pi and then to the nearest tenth of a centimeter. Okay, so how should we choose the height and the radius of this cylindrical can? Okay, so I'm going to draw this cylindrical can. And maybe I'll go like this. There's the height. So here's the height of the can. And there's the radius. Okay, and so how should we choose the height and radius in order to minimize the amount of material needed? So it seems like we want to minimize the surface area of this cylindrical can. And the surface area of a cylinder it's a closed cylindrical can, so we've got a top circle and a bottom circle, and they're both pi r squared. So 2 pi r squared for the area of the two circles. And then that sheet, sort of the middle section, comes from 2 pi r times the height. Okay, so that's the formula for the surface area of a cylinder. Okay, and so we also have that it holds 1 liter or 1,000 centimeters cubed of liquid. So our second equation is that the volume of this can is 1,000, and the volume of a cylinder is pi r squared h. So pi r squared h equals 1,000, and it's easiest to get h by itself in this case and go 1,000 divided by pi r squared. Okay. And if we take this and plug it in here for h, we will then have our surface area just in terms of r. 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And so our surface area function becomes 2 pi r squared. And then over here, the pi's are going to cancel. That r cancels with one of the r's down there. 2 times 1,000 is 2,000 over the r on the bottom. Okay, and so in terms of an interval for this function, r has to be greater than 0, because it's the radius. If it was 0, then we wouldn't be able to make a can. So r has to be greater than or equal to 0. And less than, we would look at this equation here to see if there's any other restriction on r. Mathematically, there's not. I mean, we could make r as big as we like. Even if r was infinity, it's not going to make h negative. So we're looking to see if we would ever make h negative, and we're not. So mathematically, r can get as big as we like. Okay, realistically, that's not going to work, and it's not going to minimize surface area. But that's the interval for r. And I mean, also h has to be greater than or equal to 0, and we could, in theory, make h as big as we want, and then r would be ridiculously small. Okay, but because our surface area is in terms of r, we're going to use this interval for r. Those are like our endpoints. Okay, and so to get extreme values, we have to test endpoints and critical points, so we have to get the critical points of our surface area function, which means find the derivative and find where the derivative equals 0 or does not exist. So first of all, I'm going to write the surface area function one more time in a different way. I'm going to write this as 2,000 times r to the negative 1. And now we will do the derivative. Surface area prime is going to be equal to, it's the r that's the variable. So 2 times 2 pi is 4 pi, and then the power of r would go down to 1. And this one here, we would go negative 1 times 2,000 is negative 2,000, and then that would become times r to the negative 2. So surface area prime is equal to 4 pi r minus 2,000 over r squared. Okay, and so surface area prime does not exist for r equals 0. So that's a critical point. We're going to test that as an endpoint anyway. It's not even really technically in the domain. And so then the other critical point is surface area equals 0 when 4 pi r minus 2,000 over r squared equals 0. Or that means that 4 pi r equals 2,000 over r squared, and then we can cross multiply this situation and get 4 pi r cubed equals 2,000, which means that r cubed is equal to 2,000 divided by 4 pi, but why don't we go 2,000 divided by 4, which will be 500, and then over the pi as well. So it's 2,000 over 4 pi. 2,000 over 4 is 500, so it's 500 over pi. And that means that r is equal to the cube root of 500 over pi. Okay, and then we will test our critical points and endpoints. So let's get out the red and we will go test endpoints and critical points. It's not likely that the endpoints are going to give us our minimum surface area. So we want to consider the surface area as r approaches 0. Consider the surface area of your can as r approaches infinity. And we want the surface area of the can when r is the cube root of 500 over pi. Okay, and so our surface area function is this 2 pi r business. So imagine putting 0 in for r. It would get rid of the first term, but then you'd have 2,000 divided by something really, really close to 0. So that's going to make a surface area that's infinite. And if I did infinity in for r, I would have 2 pi times infinity squared. so that's really big. Plus, you'd have 2,000 over infinity, so that would go to 0, but the first term would be really big. So those are not going to minimize surface area for us. So, our minimum surface area will come from the critical point, and we'd have to put the cube root of 500 over pi into our function there. Okay, so I wonder if we can actually graph this. The surface area function is 2 pi r squared, but we have to use x. So y is really surface area, x is radius, plus 2,000 over x. Graph that. And let's get a sense of where our critical point is. If I did math number, nope, this one, cube root of 500 divided by pi, is that 5.4. So with the window, why don't we go from 0? I don't know, let's just try 20 for now, and let's make the y max a lot bigger and see what that gives us. Okay. Volume was 1,000, so there we go. There's a better sense of it. So there's our surface area function, and you can see as r heads this way towards 0, that surface area curve is going way up to infinity, and as r heads this way out to infinity, the surface area goes to infinity. So the critical point is going to give us the minimum surface area, and I wonder if I can just calculate value. Can I put in, that would be super cool if I could. Oh, I can. The cube root of 500 divided by pi. Okay. So that looks like the minimum surface area, 553.6, let's say. That is going to be centimeters squared. And we could also check it the other way if we actually used the minimum function. Does it give us that 5.4? There we go. Perfect. That is great. Okay. So we can say the minimum surface area is 553.6 centimeters squared when r is equal to the cube root of 500 over pi. And notice it said, express your answer as an exact value in terms of pi and then to the nearest tenth of a centimeter. And so the cube root of 500 over pi is 5.4. So the r is 5.4 centimeters. And it's saying how should we choose the height and radius. So it wants us to get h as well. And h is equal to 1,000 over pi r squared. 1,000 over pi r squared. So I'm going to put the r in there. The cube root of 500 over pi, and then all of that squared. So that would be an expression in terms of pi, and I'm going to put approximately equal to, and so the height should approximately be equal to, let's see, 1,000 divided by pi times the cube root of 500 over pi. and it's actually that whole thing squared. So I'm going to have to put a bracket here, and I'm going to put, no, right here. Oh, no, I guess. Put a bracket there, because I have to square that, and then I'm going to close the main bracket on the bottom. Okay, so h is 10.8. Okay, so there's our final answer. Excellent. Let's move on to example 3. Find the area of the largest rectangle that can be inscribed in the ellipse shown there. So let's do a quick graph of this. Okay, so hopefully you remember how to graph an ellipse. The center is HK, the center is 0, 0. We go left or right the a value, which is the square root of 25. So 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And we're going to go up the b value, which is 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. So here's our ellipse. And we find the area of the largest rectangle that can be inscribed in the ellipse. So inscribed means that all 4 corners are touching the ellipse. So we would have a rectangle like this. Okay. And so the width of the rectangle is this. And the length of the rectangle is there. Okay. And we want to find the largest area. The area of a rectangle is length times width. So we need to come up with an expression for the length. And so notice, guys, that the length is basically from here to here along the y-axis. So like this would be a y coordinate length. And so you go y there, but then there's also this. So the length is 2y. And the width, we can think of going along the x-axis here. That matches up with the line width at the bottom there. You go x in this direction and the same amount of x in that direction because an ellipse is a symmetrical figure. So the width is 2x. Okay, so our expression for area is 2 times 2 is 4, x, y. That's going to be the area of that rectangle. And we need to get that just in terms of x. So the other formula there is, of course, x squared over 25 plus y squared over 64 equals 1, and we need to solve this for y. So I would subtract x squared over 25 from both sides. And we will get y squared over 64 is equal to, we could get a common denominator here if you wanted. make things a little bit simpler, I think. So y squared over 64 is equal to 25 minus x squared over 25. And then multiply both sides by 64. So y squared is equal to 64 is going to multiply onto the top. Okay, and then mathematically, y, we square root both sides, square root, and it can be plus or minus. So plus or minus. But we're actually going to take the positive y, right? Because we define our x as positive x to the right and then positive y up. So let's take the positive, and it will be there's some stuff that cancels here that might make things a little bit simpler. Doesn't cancel but simplifies. We would have the square root of 64 times the square root of 25 minus x squared. That doesn't simplify, unfortunately, but the square roots of the numbers seem to simplify. Okay, mind you, just looking at this, it might be easier to not do that. And we will go y equals the square root of 64 times 25. 64 times 25, so just distribute this in. That is 1600 minus 64x squared, and then divided by 25. And then maybe what I'll do is I'll divide the 25 on the bottom into both of those. So the 1600 divided by 25 will get us back to 64, and then minus 64x squared over 25. So that might be the simplest expression that we can have in there. Okay. So that's what y is equal to, and we're going to take this and go and plug it in here. And so now our area function is 4 times x times the square root of 64 minus 64x squared over 25. And we need to get an interval. So if we look at our ellipse, our x has to be greater than 0, but less than 5. If you look at the x, goes from 0 to 5, right? Either side. And similarly, y would have to be between 0 and 8, and I actually did that wrong at first here. This goes up to 8, right? So I sort of fouled up the ellipse right at the outset. That really should be like that. Like that. Okay, so these are our endpoints. We have to go and find critical points, which means find the derivative of this area function, find where it equals 0, or where it doesn't exist. Okay. So, let's do this. 4x we can leave the 4 out front as a constant, but x is the square root of x squared, and I'm going to write it like that so that I can multiply the x squared into this other square root. And so then our area function will be 4 times the square root. Now the x squared can now distribute onto both of these terms, and we would have 64x squared minus 64 over 25 x to the 4th. Awesome. Okay, so there's our area function, and we can write it, well, let's write it like this, 4, and then we will have 64 x squared minus 64 over 25 times x to the 4th, and then I'm going to put a 1/2 there. And now we will finally do the derivative of this. Okay, so we've got 4 times u to the 1/2 basically, so we'll do the derivative of the outside function. You go 1/2 times the 4, which is 2, and then have 64 x squared minus 64 over 25 times x to the 4th, and then go 1/2 minus 1, which will take us down to negative 1/2, and then multiply by the derivative of the inside. 2 times 64 is 128, and then that'll become x to the 1. And then 4 times 64 over 25. 4 times 64 is 256. So I would have 256 over 25 times x cubed. Over 25, I don't think that simplifies. No. Okay, so there's our derivative. That's nice. So on the top we have 2 times 128x minus 256 over 25 times x cubed. And the bottom is going to be this negative 1/2 exponent is going to flip that expression on the bottom and become positive 1/2, or which is equivalent to the square root. So there's our derivative. My goodness. And remember, x has to be between 0 and 5. Those are our endpoints. And we have to find the critical points. So a prime does not exist when the bottom works out to 0. Okay, which would mean that the inside of the square root would have to work out to 0, which would mean that 64x squared would have to equal 64 over 25, x to the 4th. And if you divide both sides by 64, that would cancel. Multiply both sides by 25, and we would have 25x squared equals x to the 4th. So x to the 4th minus 25x squared have to equal 0. We can divide out x squared and have x squared minus 25. And so this is x times x, and this is x plus 5 times x minus 5. So we would get x equals 0 out of the first two x's, we would get negative 5, and we would get positive 5. That's not in the domain. X has to be between 0 and 5. 0 and 5 are endpoints anyways, so we don't have to worry about those. Other critical points are when a prime equals 0, and a prime equals 0 when the top equals 0. 128x. The top would equal 0 when the 128x minus 256 over 25. What is it? X cubed? Yeah, x cubed. When this equals 0. Okay. And so that's 128x equals 256 over 25 x cubed. And I am going to multiply both sides by 25 and divide both sides by 128. So it would be 25x over here and 256 over 128, x cubed like that. And 256 divided by 128 is 2, so that's why I did that. So we have 25x equals 2x cubed, which means that 2x cubed minus 25x equals 0 if I subtract the 25x from both sides. And so then I can divide out an x and have 2x squared minus 25 equals 0. So x equals 0, or 2x squared equals 25. So x squared equals 25 over 2. So x is plus or minus the square root of 25 over 2. X has to be greater than 0. So x is equal to the square root of 25 over 2, and if you square root the top and the bottom, we will get 5 over root 2. There's our critical point. Awesome, so we are now ready to test endpoints and critical points. test EPs and critical points. So we're interested in the area as x approaches 0, interested in the area as x approaches 5, and the area of the rectangle at the critical point when x is 5 over root 2. Okay, where's our area function, the easiest one to work with? Maybe this guy right here. So if I were to put 0 in for x, 4 times 0 is 0, 0 times the square root will give 0. If I put 5 in for x, 4 times 5 is 20, but inside the square root, 5 squared is 25, over the 25 would just be 1, so you would get 64 minus 64, you would get 0 in the square root, so that would work out to 0. Okay, so our maximum area is going to come at 5 over root 2. And we want to find the area of the largest rectangle, so we want to put 5 over root 2 into the area function. Okay, so I'm going to put the area function into the calculator. It is 4x times that square root expression, 64 minus 64x squared over 25. I think that would be okay to do it like that. Let's make x between 0 and 5. Let's see if that helps us. Okay, so it's a little bit higher than that. Okay, good. So this is area versus x values. You can see that the area is 0 when x is 0, right over here, and the area is 0 when x is 5. And so let's go and plug in the value 5 divided by the square root of 2, and we get an area of 80. Awesome. So 5 divided by root 2 is indeed that 3.54 approximately. If we go back to the graph and use the maximum feature, do we get this 3.54 for x and 80 for the area? Perfect. Look at that. There we go. Okay. Find the area of the largest rectangle that can be inscribed in the ellipse. Okay. Max A equals 80 square units. They haven't told us the units, right? We could put this as well when x is equal to 5 over root 2. It doesn't really ask for it though, it just asks for the area. we could figure out the y as well. Y is that 64 stuff. Y is 64 minus 64x squared over 25. Square root of 64 minus 64 and then x squared, so we'd have to go 5 over root 2 squared over 25. And so we'll end up getting 64 minus, we would have 64 times 5 squared is 25, root 2 squared is 2 over 25, like that. 64 divided by 2 is 32. (25) divided by 25 cancels, so we end up getting y as being root 32, which is the square root of 16 times the square root of 2, so 4 root 2. Okay, so when x is 5 over root 2 and y equals 4 root 2. Okay, so there's our final answer for that. Crazy. All right, moving on here, guys. Example 4. An offshore oil well is located at a point W that is 5 kilometers from the closest point A on a straight shoreline. Oil is to be piped from W to a shore point B that is 8 kilometers from A by piping it on a straight line underwater from W to some shore point P between A and B, and then on to B via a pipe along the shoreline. If the cost of laying pipe is $1 million per kilometer underwater and 500,000 kilometers over land, where should point P be located to minimize the cost of laying the pipe? Okay, so let's draw a picture of this. Oops. Okay, so the black, this is the shore. And this offshore oil well is located on a point W that is 5 kilometers from the closest point A on a straight shoreline. So the closest point would be this perfect straight perpendicular line there. And they're saying that that is 5 kilometers. And we will make the oil in red. Oil is to be piped from W to a shore point B. This is the oil. Oh, sorry. B is going to be over here. Okay, so oil is to be piped from W to a shore point B that is 8 kilometers from A by piping it on a straight line underwater from W to some shore point P. So we're going to go underwater to some shore point P, which is between A and B, and then on to B via a pipe along the shoreline. So then along like this. So the oil is going to go on red like that. Okay. And it's just saying that the point B is 8 kilometers from A. So that whole thing is 8 kilometers. Okay, and so it comes down to where should point P be located to minimize the cost of laying pipe. So we want to know what that X distance away from A should be. And if that's X, since the whole distance from A to B is 8, then this would be 8 minus X. And we can think of this as 90 degrees. Okay, and so the cost to transport oil for a certain distance is going to equal the cost per kilometer times the number of kilometers. Okay, or like the distance that the oil is piped. And so the oil is piped from W to P. This distance here, D squared equals X squared plus 5 squared, so the D would be the square root of X squared plus 25. Okay, and so this is the distance under the water, and the distance the oil is piped along the shore is equal to this 8 minus X. Okay, and so the total cost of this, let's call it C, is equal to, it's going to be $1 million per kilometer times the distance in kilometers that the oil is piped underwater, and that is this, right? Square root of X squared plus 25. Plus, it is $500,000 per kilometer times the distance that the oil has to be piped along the shore, which is this, 8 minus X. Okay, and what we can do, guys, actually to simplify this is we can treat our units as millions of dollars. And what I'll do is I'll say the cost is, it's $1 million per kilometer times the number of kilometers to go underwater, which is that, plus $500,000 is $500,000. So I'm treating my cost units as millions. $500,000 times 8 minus X. So I have to understand that my answers for X are going to be in millions of dollars. Okay, so there's our cost function. X has to be greater than or equal to 0, but less than or equal to 8. Okay, because we're not going to pipe the water underground past the point B, like beyond the 8 kilometers, and then go back. So it's somewhere between A and B, like the 0 and 8. All right, so these are our endpoints. We just need to find the critical points and then do our little tests. Okay, so we need to find the derivative of this. Now, the cost function is x squared plus 25 to the 1/2. And I'm going to distribute this through, make that a bit simpler. A half times 8 is 4, and a half times negative x is negative a half x. And now let's find the derivative. We would go a half times x squared plus 25 to the negative a half times 2x, the derivative of the inside. The derivative of 4 is 0, and the derivative of negative a half x is negative a half. So c prime is equal to a half times 2 is 1, so we're going to get x over the square root of x squared plus 25 minus a half. Now, is there anything that's going to make 0 on the bottom of that fraction? There's nothing I can put in here for x that will make that expression on the bottom 0. Okay. So we don't have to worry about c prime not existing. So c prime equals 0 implies that we set this thing equal to 0, which means that x over the square root of x squared plus 25 equals a half. And now let's cross multiply. 2x equals the square root of x squared plus 25. Square both sides. So I did squaring both sides here. And then we'll get 3x squared equals 25, so x squared equals 25 over 3. So x is equal to plus or minus the square root of 25 over 3. X has to be greater than or equal to 0, so x is going to equal the positive square root. The square root of 25 is 5. Square root of 3 we'll just write as root 3. And this is equal to approximately 5 divided by the square root of 3, 2.89. Okay, so now let's test endpoints and critical points, and we are looking for the minimum cost. So the cost, if x was 0, the cost if x is 8, so what that means is pumping the oil underwater the whole way. And the cost at the critical point, 5 over root 3. All right, let's get out our calculator. Let's do the cost function. It is the square root of x squared plus 25 plus 4 minus a half x, or x over 2. And we'll graph that. Okay, so I graphed this cost function right up here. Oops. And let's go zoom, window, we're going to go from 0 to 8, and we'll just shorten this a little bit. Maybe make that 12, let's see what that does. Okay, so what is the cost when x is 0? So that means just going straight perpendicularly to the shoreline and then along the shoreline. We get a cost of 9. Remember, that's in millions of dollars. $9 million. Cost of x being 8, so going straight underwater to point B is $9.4 million. And at the critical point, 5 divided by the square root of 3, we get $8.3 million. Awesome. There's our minimum cost. Okay, so where should point P be located to minimize the cost of laying the pipe? So minimum cost equals $8.3 million when x is equal to 5 over root 3, which is about 2.89 kilometers, because that's in kilometers. X okay, so x is that, and so that's the distance that P should be away from A. So P should be 5 over root 3 5 over root 3 kilometers away from point A. Okay, or you could even figure out how far away it should be from point B. However you want to do it, it would just be 8 minus that 2.89. 8 minus 5 over root 3. There's the distance that it is away from point B. Awesome, we continue to motor. Good, we already did number 5. Number 6 is very similar to the last two there. The famous lifeguard problem. A swimmer is in trouble at the beach. The swimmer is 50 feet offshore. Okay, the swimmer is 50 feet offshore and 150 feet downshore from the lifeguard. Okay, this is 150 feet. If the lifeguard can run along the shore at 6 feet per second and can swim at 3 feet per second, how far down the shore should he run before starting to swim in order to minimize rescue time? Okay, so the lifeguard is going to come along here to some point P and then swim the rest of the way. Okay, so what you do is make this x. This is 150 minus x. This is the distance he has to swim. D squared is equal to x squared plus 50 squared, so d would be the square root of x squared plus 50 squared. And this is the distance he has to run. There you go, buddy.
What are you doing?
Okay. So distance equals speed times time. Time is equal to distance over speed. His speed of swimming is 3 feet per second. Speed of running is 6 feet per second. Okay, so total time is equal to time to run plus time to swim. Time to run is going to be distance to run divided by speed of running plus distance to swim divided by speed of swimming. Total time function, his distance to run is 150 minus x. His speed of running is 6 feet per second. Distance to swim is the square root of x squared plus 50 squared, which is 2,500. And speed of swimming is 3 feet per second. Okay, and our interval, x has to be greater than or equal to 0, less than or equal to 150. There's our interval, those are our endpoints, and let's go and find the critical points. So first of all, the t function is 150 divided by 6 minus, or negative x divided by 6 is minus 1/6 x, and then plus, we will have 1/3 in front of x squared plus 2,500 to the 1/2. And now let's do t prime. The derivative of a constant is 0, so the derivative of that is 0. The derivative of this is negative 1/6. And the derivative of the last part, you'd go 1/2 times 1/3 is 1/6 times x squared plus 2,500, and 1/2 minus 1 is negative 1/2, and then times the derivative of the inside, which is 2x. Okay, we need to set this equal to 0 and solve. Okay, 2 over 6, we'll make that a 1/3. Let's go, t prime is equal to, we've got 1 times x on the top there, so just x on the top. And on the bottom, we would have the square root of x squared plus 2,500. And then we've got this minus 1/6. So I just switched the terms around. Oh, and we have this 3 on the bottom here as well, still. Okay, so 1 times x on the top is the x. We've got the 3 on the bottom. Negative power of 1/2 becomes positive power of 1/2 on the bottom, which is the square root of that. And then we've got our minus 1/6. Does t prime not exist anywhere? We'd have to get 0 on the bottom x squared is either 0 at the smallest or positive, so there's nothing we can put in for x that will make 0 on the bottom, so we just have to set this equal to 0 and solve. So we will have x equals 1/6, like that. Let's cross multiply. And we will get 6x equals 3 times the square root of x squared plus 2500. Maybe we could divide both sides by 3. And we get 2x equals the square root of x squared plus 2500. And now we'll square both sides. So 4x squared is equal to x squared plus 2500, so 3x squared is equal to 2500. And so x squared equals 2500 over 3. And so x, because it has to be greater than or equal to 0, is just going to be the square root of 2500 over 3. I guess technically we should show plus or minus and then say that it's this, and reject negative. The square root of 2500 is 50, and the square root of 3 is like that. Okay, so now let's test endpoints and CPs. We are interested in how long this takes when x is 0. What was my interval up here? Between 0 and 150. How long this takes when x is 150. And the time for our critical point, 50 over the square root of 3, which is 28.9. Okay. So if we put in our time function, it is 150 over 6 minus x over 6 plus the square root of x squared plus 2500, and that was over 3. Okay, and x has to be from 0 to 150, and maybe I'll try that. Our time is going to be in seconds because they gave us speeds in like feet per second, okay, and distances in feet, so we're going to end up getting seconds for the time. Okay, so what is the time if x equals 0? We get 41.6 repeating seconds. Time for x equals 150, 52.7 seconds. And is our critical point going to be the best time? 50 divided by root 3, 39.4 seconds. So yes, that's the best time, but just barely, and just a little bit better than x being 0. So we can say, therefore, minimum T is 39.4 seconds when x equals 50 over root 3, which is 28.9 feet. So technically, how far down the shore should he run before starting to swim? He runs down the shore 150 minus x. And x was this 50 over root 3, right? 150 minus 50 over root 3. Okay, so he should run 121.1 feet down the shore. He should run 121.1 feet down shore. Okay, and it says here the calculus dog, and I think there was an article that sort of talks about how dogs will actually do this when you throw a stick into the water. They'll run along the shore first and then they'll start to swim. And it's sort of interesting that perhaps the dogs know a bit of calculus to do that. Okay, and then in the textbook it talks about economics problems. Important functions to economists and manufacturers are the cost function, C of x, total cost of producing x units of a product during some time period. The revenue function, R of x, equals total revenue received from selling x units of the product during some time period. And the profit function, P of x, is the total profit obtained by selling x units of a product during the time period. If all units produced are sold, then these functions are related by profit equals revenue minus cost. The total cost, C of x, of producing x units can be expressed as a sum, C of x equals A plus M of x, where A is a constant called overhead, and M of x is a function representing manufacturing cost. The overhead, which includes such fixed costs as rent and insurance, does not depend on x. It must be paid even if nothing is produced. Manufacturing costs include such items as cost of materials and labor, and therefore do not depend on x. Therefore do depend on x, the number of units produced. Furthermore, it is shown in economics that with suitable simplifying assumptions, that M of x can be expressed in the form M of x equals bx plus cx squared. Therefore, C of x is equal to A plus bx plus cx squared. Okay, because you're taking this and you're plugging it in there, which would be right here. So, if a manufacturing firm can sell all the items it produces for P dollars each, then its total revenue, R of x, will be R of x equals P times x. Hence, its total profit will be total revenue minus total cost, so P of x minus A plus bx plus C times x squared. So, example 1, a liquid form of penicillin manufactured by a pharmaceutical firm is sold in bulk at a price of $200 per unit. If the total production cost in dollars for X units is C of X there, and if the production capacity of the firm is at most 30,000 units, in a specified time, how many units of penicillin must be manufactured and sold to maximize profit? Okay, so profit is equal to revenue minus cost. Revenue is number of units times the price. So $200 per unit for X units minus the cost is this 500,000 plus 80x plus 0.003x squared. And so we can simplify this. And let's distribute the negative. We would get negative 0.003x squared. It would be 200x minus 80x, so plus 120x, minus 500,000. Okay, and the number of units that you are going to sell certainly has to be greater than or equal to 0. We can't sell negative units, so we're either going to sell 0 or above. And it says the production capacity of the firm is at most 30,000 units at a specified time. So we can't go beyond 30,000 units. So that's the interval for X. I'm going to sell anywhere between 0 and 30,000 units. Okay, and so how many units of penicillin must be manufactured and sold to maximize the profit? So are we going to maximize our profit if we sell 0? Are we going to maximize profit if we sell all 30,000 or somewhere in between? So these are the endpoints. We need to find the critical points of this function, so find the derivative. Find where the derivative equals 0. Okay, divide both sides by that negative 0.006. So I'm going to go negative 120 divided by negative 0.006, and we get 20,000. So now we will test EPs and CPs. We want to see the profit when X equals 0, the profit when you sell all 30,000 units, and the profit at 20,000. Okay, so why don't we try graphing this? Profit is equal to negative 0.003 and then x squared plus 120x minus 500,000. Okay, so X needs to be between 0 and 30,000. try that interval, and there is our profit function. Awesome. Okay. So, profit for 0 units is negative $500,000. If you don't sell anything, you still have your costs. Okay, so you're in the hole, $500,000. What is your profit if you sell 30,000? $400,000. And what is your profit if you sell 20,000 units? There's your best profit, $700,000. Okay, so how many units of penicillin must be manufactured and sold to maximize the profit? Max P is $700,000 when X equals 20,000 units. Okay, there you go, everybody. We are finally finished these extreme value problems and these notes. We'll keep working on them. I would encourage you to read the textbook, try the questions that I've assigned, check out my handwritten answer key, and next week we can go on to something new, which I think is a whole lot easier than this, and we'll kind of go from there. Okay, I will talk to you soon, everybody.